So, wait 1 more minute, I think. Okay, so I'll get started. So let's continue talking the parameter redundancy. So so the goal of the our AR model, AR-MA model construction is that we want to find the simplest AR-MA model, and but there might exist some parameter redundancy problem, and the solution to that is that we put the AR part on the left-hand side and the MA part on the right-hand side, and check if there is any redundancy. Okay, so here's an example. So the model is xt equals 0.3 xt minus 1 plus 0.4 xt minus 2 plus wt plus 0.5 wt minus 1. So this is a ARMA21 model. Okay, and we want to check if this model has the redundancy problem. Okay. So we put the AR on the left-hand side. So it's minus 0.3 minus 0.4. And the MA part is and we will write it in using the backshifter representation. So this minus 3b minus 4b squared xt. And this is, I think, 1 plus 0.5 wt. No, sorry, 1.5b. Okay. So what we want to check is we basically want to check if this part and this part has some overlap. So let's do some decomposition on the left-hand side. Okay, so the left-hand side, it can be written as 1 plus 0.5b, 1 minus 0.8b xt. Okay. So you can see from here that the left 1 plus 0.5b and the right-hand side also have 1 plus 5.5b. So that means these two terms can cancel out. And we actually do have a parameter redundancy problem here. Okay. So the reduced model now is xt minus 0.8 xt minus 1 plus wt. And this is just a ARMA11 model. And we want to choose this as our final model. Okay, so in it is usually not easy for you to do this kind of like decomposition to find the overlap terms in the AR part and the MA part. So what we usually do is that we ask the computer to do this for us. Okay? So basically, it's to ask the computer to find like the root of like the AR polynomial and the MA polynomial and see if the root has some overlaps. And if they do have some overlaps, so for example, here, the overlap is that 1 plus 0.5b. So b is going to be negative 0.2. So if it does have some like overlaps, then we will say that there is parameter redundancy problem. Okay. So I will show you an example later, but I want to first finish remarks of the ARMA model. So okay, so that's pretty much the parameter redundancy. Okay, so the last remark I want to do is ARMA to AR or MA format. Okay. So sometimes once you estimate an AR model or you construct an AR model, you want to know its like its causal form or its invertible form. So in other words, you want to know its MA or the AR representation. Okay. This AR representation is its causal format. And we also want to know its MA representation. This is, no, I do it wrong. So this is the invertible. The invertible representation, and this is a cause. That's okay. So sometimes we want to know that the AR representation or the MA representation of our model, because we know that if our model is a valid AR-MA model, we can always write it as a infinite AR representation or a infinite MA representation, and we might the coefficients of the AR representation or the MA representation. Okay, so in practice, I mean, to solve like those coefficients by hand is extremely complicated, unless that model has a very special representation. So for example, if it is an AR1 model, then we know that the coefficient of the infinited MA model is just like the coefficient to the power. So that's easy, but in most cases, it's relatively hard to find like to find the closed form solution of all the coefficients of the AR representation or the MA representation. So in those cases, we can again ask the R to find the coefficients for us. Okay. So we will use R to find the AR or MA representations. Okay, so I think to give you examples of two examples. One is about the parameter redundancy, how to check it using R, and also another example is about how to change the ARMA to its AR or MA representation. Okay. So let me get back here. So that's first install the library. So this first example is to check parameter redundancy. Okay. So this is basically the example that I gave you in class. So the AR part is this AR2 model. So it's xt minus x 0.3 xt minus 1 minus 0.4 xt minus 1. Okay, so we can use this code, the polyroot, to check the root of that polynomial. Okay, so what we got is 1.5 and minus 2. So I think this would be exactly the same as the one that we solved by hand. Okay, so the roots are 1.5 and -2. Okay, so these i's are just the complex part. So in our case, we do not have imaginary solution. So that's perfect. Okay. And the MA part here is WT plus 0.5 WT minus 1. So, and we again ask we ask the computer to use this polyroot command to solve the root of this MA model, this MA polynomial. So the root is -2. Okay. So we find -2 is the common root in AR and MA polynomials. So they suggest this parameter redundancy problem. Okay. And notice that this number is like the fake number. Okay, so it's just an example number. So you get exactly two same roots, so -2 and -2. So they're exactly the same. But in practice, especially when you are running the real data, so you, in most cases, you cannot find like the exactly two same roots. So what you will do is that if you find like two roots are very close to each other, then you will think that there might exist parameter redundancy problem. Okay, so in real applications, if the roots from AR and MA polynomials are close, then there is parameter redundancy problem. Okay. Okay. Let's see. Yes. So I don't know if you write this down or not, but remember the MA part is 1 plus, I do not go back to the whiteboard. So okay, let me just type here, okay. Okay, I'll just type in R. So just to, if you like copy what I just wrote down on the whiteboard, you can check. So in the MA, what we have is 1 plus 0.5b, right? 1.5b WT, right? So that's the MA part. And the MA polynomial is 1 plus 0.5b. Okay. So the root is what? So the root is 1 plus 0.5b equal to 0. So that is b that would make this like polynomial. This is just a linear model. This linear model equal to 0. So that is b is equal to -2. So which is exactly what we want here. Okay. AR polynomial. So the AR polynomial we got is 1 plus 0.5b, 1 minus 0.8b. Okay. Or let me write it maybe in this way. So this is a polynomial, 1 minus 0.3b minus 0.4b squared, okay? And we can write this like order 2 polynomial as 1 plus 0.5b times 1 minus 0.8b, okay? So the roots here, there are 2 roots here. One root are 1 plus 0.5b equals 0, and 1 minus 8b equals 0. Okay. So they suggest that let's say b1 equal to -2, so which is b that makes this equation equal to 0. Okay. And b2 is 1 over 0.8, so it's 1.25. Okay, so which is a number that make this polynomial equal to, or this equation equal to 0. Okay, and you can see that this is just what the computer does. So it finds 2 roots. The first root is 1.5. The second root is -2. Okay, so it's exactly what we got by using hand. Okay. So why I say that we want to use computer, because like in real data, you really can find such nice roots. So what you estimate to be a very, very weird numbers. So to find the roots by hand might be hard. And if like the polynomial is high order, say like order number 3 or order number 4, then to find the roots becomes even harder. So that's why we want to ask the computer to find the root for us. Okay. And I also point out that in real applications, we really can have like -2 here. But if you find like the roots from the AR and MA polynomials are very close to each other, then this would just suggest you have the parameter redundancy problem. Okay. Yeah, I think how close is close? How close is close? Yeah, that's really a good question. I don't know. I do not know actually. So, but I guess if it is like smaller than 0.1, then that should be considered as close. That also depends on like the actual number you have, right? So if it's like 5 or 4.9, I think that should be considered as close. Okay, yeah, so that means that you need to rerun the model. Okay, so that does not necessarily mean that your model is not correct. So you understand what I mean? So suppose that you start with a ARMA33 model, and you encounter this parameter redundancy problem, and you find like root is very close to each other. So they suggest that you might to run a ARMA22 model. And once you run the ARMA22 model and you check, okay, there's no parameter redundancy problem, then the next step is not to say that your AR22 model is strictly better than AR33 model. You also have to check like all those stuff, like the AIC, BIC, and the residual plots. Okay, and from there, and if you do find that the AR22 model is not as bad as, I mean, it's as good as the AR33 model, then you can conclude that the AR22 model is a better one. But however, if you find like the residual plots or the AIC or the BIC, and also I think the coefficient significance of the ARMA22 model is worse than the AR33 model, then that means you probably should still stick with your AR33 model. Okay, so that's just like a iterative step. Okay, so you need to do like all this stuff like iteratively and find the best model. Okay, yeah. Yeah, so I mean, like in practice, you encounter a lot of like such problems, and the more you do the analysis, I think the better model you can choose. Okay. Okay, so I think everyone should be fine with this. Everyone good with this. Okay, so the next example is to find MA or AR representation using ARMA model. Okay. So these are the two examples. So this is the AR11 model with AR part 0.8, MA part negative 0.5. Okay, so let's check. Let's first like switch it from ARMA to MA, and let's find the first 10 coefficients. Okay. Okay, so this is what we got. So we start with 0.3, then 0.24, 0.192. Yeah, so you can see that this coefficient decreases. Okay, and if you, I think if you increase this, I guess you see a better pattern. It's like decreases, or I mean, in other words, it would converge to 0. Okay, so this suggests that this MA representation is good, because in the MA representation, we want like all this, the summation of all these coefficients is finite. Okay, so if it does not converge to 0, then the summation cannot be finite. Okay, so if like all the coefficient is like say 0.2 or 0.3, then 0.3 times infinity is infinity. So you have some convergence to satisfy the convergence requirement in the MA representation. Okay, so this is good. So this is the MA coefficients converge to 0. So which is good. Okay, and now let's check the AR part. Okay, and again, you can see the AR representation is also good. It also converges to 0, so which means our model is invertible, so which is good as well. Okay. All right. But how about this one? So we know this is like AR, this is an ARMA 10 model. And the AR part with coefficient 1 and the MA with coefficient 0. So it's just xt equals xt minus 1 plus wt. So this is a random walk model. And we know it is not stationary. It's not causal for sure, because the coefficient is equal to 1. It's not strictly less than 1. Okay. So this is a non-stationary model. And let's check if I want to find its MA representation, what I will find. So you can see that all the coefficients are equal to 1. It does not have like such convergence pattern. Okay. So this again tells us that our model is not good. it's a not ARMA model. It's not a valid ARMA model. It's still an ARMA model, but it's just not has like the causal and invertible properties. So it's not a valid ARMA model. So this is another station model, and not a station model. So we know, just 1 second, please. So we know from theory it is not a stationary model. The R output shows the same. Okay, so what is your question?
So for the beginning, we just need to show that it converges to 0 to conclude that it sums to less than 1.
Yeah, that's I think a typical and easy way to check. Yeah.
Okay. Why is it that tends to work out?
Oh,
I could construct a whole bunch of series that converge to 0 that don't add up to.
You have a convergence theory that is not finite? Is that your question?
Yeah, like I feel like I could construct series that converge to 0, but add up to much more than 1.
No, not more than 1 is to be finite. I think any convergence, maybe, I'm not exactly sure, but I think for most convergence sequences, the summation should be less than infinite. So it's gonna be a finite thing. If it is converged to 0, yeah, if it converges to 0, then the summation gonna be finite. If it converges to 1, then it's definitely not.
Yeah. But then we want the summation to be less than 1, right? Of all of the coefficients.
No, the summation less than infinite.
Oh, less than infinite. Okay, thank you. Sorry about that.
Yeah. So I'll give you more. MA coefficients converges to 1, so it's more specific. The summation of all the coefficients is less than infinite. So this is a good model. Summation of all the coefficients is less than infinite. Good. Okay. The output shows the summation of all the coefficients are infinite. So this implies not causal, not station. Okay, so any questions here? Okay, so I think that's the ARMA model. Yeah, so to have a valid ARMA model is not easy. So once you like estimate a ARMA model from your data, you have a lot to check. So you have to check the coefficients. You have to check like it's causal or it's invertible. You need to check whether there's any parameter redundancy. Okay, and of course you need to check the residues to see if it follows a white noise pattern. Okay, so yeah, so anyway, so that's pretty much like the setup of the ARMA model. So any questions? Okay, so if there's no questions, I think I want to do a quiz here. Okay, so let me start the poll. Okay, so this is the first question. Asks you whether this is invertible or not invertible. So this is an MA model. The coefficient is 0.8. It's MA1 model. Okay, let's have another 30 seconds. Okay, I think that's it. Okay, so yeah, the answer is true. So the reason is that this 0.1 is less than 1. Okay, yeah, so very straightforward, I think. Yeah, I just want to maybe re-emphasize or point out again, so that why we want to need like invertible or why we want to need causal. So yeah, you might wonder, we talk about this a lot, but why we want that? We know that it has good properties, but why we want that? We know that if it is causal, it has like a infinite MA representation. If it is invertible, it has infinite AR representation. We can use like the previous values to predict the current value. Yeah, so that's all the reasons that we want a vertical model. And another very important reason, and we haven't talked about that yet, but another very important reason is that like without this invertible or the stationary assumption, you basically cannot do the estimation. Like all estimation just fails because the reason, just remember that in your cross-sectional data, you need the data to be IID, right? In order to do like those expectation or to find the variance to derive all those stuff, right? To derive the properties of the estimators. And here is the same thing. So without the stationary and the invertible, they're doing like such type of regression. So if you just, so this is not a regression, there might be a regression. So like in the AR model, and if you want to do the regression of xt on xt minus 1, that's not correct. You definitely can do the regression, but I mean, the theory behind that regression is just not correct without having this stationary and invertible properties. So that's why we really care about the stationary and the invertible. So all the estimations we have are built on this. So if you do not have this, that's totally just like cross-sectional data. So without the IID assumption, everything fails. I mean, most things fails. You need to have some extra things in order to run the regression. Okay, so that does not mean like if I can run the software, then we are good. That's not the case. So we need like those stationary and invertible and also causal in order to run all those stuff. Okay, so I just want to be clear to not make you lose why we want like invertible and stationary. Okay, so that's question number 1. I think very good. And there's question number 2. Okay. Okay. So this you might spend some time to solve it. Okay, so I ask you if this has parameter redundancy problem. Okay. So this is an ARMA22 model. let's have another, maybe 1 minute, one more minute. I think I will also poll. Okay, so good. Okay. Yeah, I think, yeah, sorry, but yeah, I think you all got this. No, most of you got this. It's gonna be true. To find. Okay, so to check this, you can just use like your, let me close this. You can just check like using your laptop, or you can definitely check by hand, but I mean, using the laptop is also easy. So that's the AR part. The root is 1.111 and -2. And I think the MA part, this is 1 and 0.25. Okay, so -2, -2. So 2 roots. So you have like -2 and -2 exactly the same. So this suggests there's a primary redundancy problem. Okay, so any questions? Okay, so okay, I don't think. Okay, great. Okay, so now let's move on to the next topic. Okay, so the topic we just discussed about ARMA is the theory of ARMA. So we want to know what's the requirements that the ARMA model needs. Okay, so we know that it needs to be causal, it to be invertible, and it also needs to have like that setup. So the AR part and an MA part. Okay, so the next question is that what AR-MA model we need to choose? Okay, so we know that the AR has some order, the MA also has some order, but what orders we want to choose? So can we, if I have a raw data set, so what's AR-MA model I want to use? So that's the next question. And from the previous slides, I think we have like that type of table. Okay, so we say that if the ACF cuts off at say like number Q, then that means we will have a AR number P, I guess. We will have an ARP model. And, no, sorry, it cuts off, the ACF cuts off at Q, then we'll have MAQ model. And if the PACF cuts off at the lag number P, then we will have an ARP model. Okay, so we have that table. I showed that table before, but why that table is true. Okay, so in today's class and possibly next class, we will discuss why that table is true, and I will present that table again, and that table would help you to choose the ARMA model. Okay, so let me switch to the, okay, let me switch to the whiteboard. So the readings for so the readings of this part is SS 4.2, BK 3.2.4. Today's R and slides. The slides is not that comprehensive, so can read 34 to 40. Okay, so let's answer this question. So what AR, MA, Q we want to choose? Answer. We will use ACF and ACF to choose P and okay. So let's start with ACF. Okay. So start with ACF. Let's first start with the ACF MAQ model. So the MAQ model is this. So that's the MAQ model. And let's find its autocovariance. So this would be equal to so that's autocovariance. And we know how to find the covariance of this, right? Basically, we just define like how many white noises are overlapped in these two summation sites. Okay, so we can find that. Okay, and again, let's just assume the variance of each white noise is sigma W squared. So we can find this. So if H is larger than Q, then the autocovariance is 0. And if H is less than Q, larger than 0, then the autocovariance is this top formula. So it's not equal to 0. That's a key point. So it's not equal to 0. It's sigma W squared times some productive of the summation. Okay. So that tells us what? So that tells us the cutoff, like for a MAQ model, the ACF would cut off after Q legs. Okay, so conclusion. Conclusion is this. So cutoff gamma H QLEX. So that is all the autocovariance after QLEX is 0. Okay, so that's cutoff of the autocovariance after there's cutoff of gamma H after QLEX. Okay. And in practice, if we find so in practice, if we find the first Q autocovariance outside the 95% confidence interval, so we know the ACF confidence, the standard error of the ACF is 1 over square root of t. So the 95% confidence interval is approximately positive -2 over square root of t. Okay, so if we find that the first Q autocovariance are outside of this confidence interval, and the rest are within this confidence interval, then that means the model we are looking at should be a MAQ model. Okay. Okay. And this is just so the conclusion of this. I mean, this conclusion is just come from what I just showed. Okay. The autocovariance function of the MAQ model. Okay. Okay. Now let's see what about the ACF for a ARP or a ARMA model. Okay, so ACF so we will consider this two cases just at the same time. Okay, so we first write or RMRPQ in its MA representation. So why can we do this? Because we assume our ARMA model is a causal model. So that means we can have a MA infinite representation. Okay. Number 2, find gamma H, the autocovariance function. So if you just find like overlap of the white noise between xt plus h and xt, you'll find the autocovariance is just this form. Okay, the key point is it never equal to 0. So it's never equal to 0. That's it. It's just sigma w squared time summation. Okay, it's never equal to 0. After maybe p lax or q lax, it's never equal to 0. Okay, that's a key point. Okay, and this also suggests that the autocorrelation function is never equal to 0. Okay. So, conclusion. So the ACF of ARP or a ARMA PQ model does not have cutoffs at any lax. Okay. So this suggests that using ACF to determine is hard. Okay. But I mean, even though this autocovariance function is not as informative as the autocovariance function of the MAQ model, but it still gives us some information. Okay. So the information comes from this psi. So remember that the requirements of the psi is that we want the sum of the psi or the square of the sum of the square of the psi is less than infinity. Okay, so as we just showed in the R, so in order for that requirement to be true, like the farther the larger the psi would converge to 0. Okay, as like its index increases. Okay, so it still provides us some information. So let me have another page. So we would expect that the autocovariance function would have some work like a decreasing patterns, or this decreasing pattern would decreasing to 0 as the number of lags increases. So as h increases. Okay, so this is sometimes also called tail solve. So the tail is never, but it would converge to 0. So that's what this means. Okay, and why? This is because we require psi j squared less than infinity. So psi j would be small as j goes to infinity. Okay. And furthermore, So that's the reason. Okay. Yeah, so the reason basically comes from, again, the requirement of having a causal model. So we want the psi j, the summation of the psi j squared to be less than infinite. Okay, so that means the psi j decreases as j goes to infinity, and the coefficients on our autocovariance would also decreases as h goes to infinity. So we would expect to see such tails of pattern in the ACF plot. Okay. Yeah, but this is not as informative as the ACF plot for the MAQ model, because for the MAQ model we can like determine the order Q, but here we only know that it just tails off, but it does not provide us any information about the order P. Okay. Okay, yeah, I think here I have this example. So let's do an example here. AR2 example. So in this example, we can write xt as this. Okay, so there's actually a closed form solution for this AR2 model, a closed form solution for this AR2 model. So this psi j, when j is 0, is basically this cosine function. Okay, and the period of this cosine function is 12. Okay, so that's why people sometimes say that it will like be sine of or cosine of, because in some cases, especially like for this AR2 process, it has like this cosine waves. So this psi j is not equal to 0, but it would converge to 0 in a cosine way, and the period is 12. So that's what the coefficients here suggest. Okay. Yeah, but again, unfortunately, this psi 0 and this psi j does not provide us any information about order number 2. Okay, so we cannot get AR2 by looking at the ACF plot. Okay. So the question now is, how can we determine the order of the AR part of the ARMA model? Okay. The answer is that we will use PACF, partial autocorrelation function. Okay, so we talked a little bit about the PACF earlier, so just for that, what is a PACF? Okay. So the PACF of xt and xt minus h is the correlation between xt and xt minus condition, everything between them. So xt minus 1, xt minus 2, all the way to xt minus h plus 1. So that's the PACF. Yeah, there are a couple of ways that you can find the PACF from your data. So if extent xt minus h are linearly related, then PACF is the coefficient of xt minus h of the following regression. So it's xt beta 0, beta 1, xt minus 1, beta 2, xt minus 2, beta h, xt minus h. So it's basically this coefficient. So beta h captures the conditional correlation between xt and xt minus h. Okay. So that's the PACF, and we also has a property of the PACF. So it's the asymptotic theory of the PACF, just as the ACF. Okay. So that is okay. Let's if a time series So that's a property. It's a symptotic property. So it's same part. It's a standard error. It's a standard deviation. So it says that if a time series has several properties, then when the h is less than the order of your time series, then the PACF h is a approximately, and its mean is 0, and its standard deviation is 1 over the square root of t. So it's basically the same as the property of the ACF. So the ACF, we know that it's asymptotic standard deviation is also 1 over square root of t. So for the PACF, it's basically the same story. Okay. So now I think, yeah, let me finish this. Okay, so probably I don't have enough time. So let's just give an intuition. So how can we use the PACF to find the order of the ARP model? Okay. This is just an intuition. Okay. So suppose our ARP model is this. Okay. It's a very standard ARP model. Okay. And if H is larger than P, okay, so just have a number H, then the PACF of order H is equal to 0. So why this is the case? Because if H is larger than P, then this xt minus H, so this variable, is not in this ARP model. So it's not in this regression model. Okay. So since it's not in this regression model, which suggests that its coefficient should be equal to 0, right? So why? Because xt minus h is not in the ARP model. So which means its coefficient, so which is PACFH, is 0. Okay. So this gives us somewhat a conclusion or a practical way to determine the order P by looking at the ACF. Okay. So if we find if we find the PACF of the first PLEX within this confidence interval, positive, negative 2 over square root of t, and the rest within this confidence interval, then this is an ARP model. Okay. Yeah, so what I just discussed is not a formal proof, but I mean the formal proof somewhat like follows the same intuition. Okay. So let me do a quick example and end today's class. So for example, let's xt equal to 1.5 xt minus 1 minus 0.75 xt minus 2 plus wt. Okay. We can solve PACF1 is equal to 0.86. Okay. PACF2 is equal to negative 0.75, and H is equal to 0 for all H greater than 2. Okay, so this is exactly what we have. So since it's an ARP model, so that means the first two PACF is significantly different from 0, and the rest of the PACF is just equal to 0. Okay. So any questions? Okay, so in next class, we will discuss the PACF of the MAQ, and you can expect that it does not provide us any information about choosing Q by using PACF. And I will do some R codes and conclude this part. Okay, so I think that's it for today's class. I will see you next Monday. Thank you.